Hello, my name is Richard Collins, and I was looking at a series of papers related to magnetic birefringence in the vacuum. I traced down several different pathways, and particularly this one interested me, the BMV experiment. And by looking through some of the background for those and all, I came across your dissertation, which I thought was quite interesting. The I don't know much about the experiment you were discussing. I have a lot of these studies to look at. I'm reviewing all the technologies that are reaching a certain sensitivity, and I let me just keep going. So anyway, this is where I thought I would contact you. This looked very familiar. There's a small group of people working on the relationship between the energy density in a magnetic field and that in electric and gravitational fields. And the rough equivalence, if you take the energy density for the gravitational field at the surface of the Earth, it's equivalent to about 380 Tesla. So, give you an idea. The the impact, though, the more immediate reason I thought you might be interested is I calculated the change in clocks at your location because of the changing um, gravitational potential there, and also I calculated roughly the change in the tidal gravitational field at that location in Toulouse. I don't know. There seem to be several experiments going on around Toulouse, and so I just used that as my central point. The data I use, the method I use for this, I've been doing this for about 15 years. So um, I I started with the superconducting gravimeter network, and I used this method to calibrate those. And then I've gone through the seismometer network, and at least the broadband seismometers will pick up a very clear signal. Let's see, do I have one that I can show you? Okay. Maybe I'll come back to that. Hang on a minute, just a moment. Sorry for the delay. they, this is the tidal gravity at Matsushiro, Japan, for the vertical axis. That's all they have for a superconducting gravimeter, minute by minute for whatever period this was. This was. I'll have to go look when this one was done. They've been running these for many, like decades now in some cases. You can just see, here's a spike in here, which is probably a small earthquake there in Japan. And in the background, you can see the residual between the calculated signal from the sun and moon. It's a vector tidal gravity or vector tidal acceleration. The sun acting at the station minus the sun on the center of the Earth, plus the moon acting at the station minus the moon at the center of the Earth. That very simple Newtonian calculation gives a very good fit. I say roughly it's about 95% of the signal at a superconducting gravimeter station, and then the residual is where all of the Earth-based activity is left, and that's why I do it, because who needs to be following all these variations just from the sun and the moon. So you subtract those out and then just work with the residual. So it turns out you can do the same thing with broadband seismometers. And in the past couple of years, there's been an explosion of detectors that can track this signal. MEMS gravimeters are one of the first ones that were tried. Atom chip, which based on atom interferometer techniques. There's a lot of those. And actually 2 or 3 more that I've just found and I'm trying to trace down. So the number of groups working on this is just, I can't keep up with them hardly. It turns out though that let's see which way I should go here. So where does this come from? Let me do a quick background on that. Besides these are what I call, these are the gradient of the Earth, the potential. So these are the acceleration term. But in addition to that, there are daily variations in momentary changes in the rate of clocks at the surface of the Earth because of the changing potential from the sun and the moon, and actually from the shape of the Earth as well. So let me see if I can show you that. This is crude. I was in the middle of another calculation for someone else. This is roughly what, there's a term missing in here, but this is roughly what Toulouse for April. Okay, so that's roughly what the acceleration term looks like. And if you aren't correcting for that in an experiment, in many experiments, then you're going to get odd results. And so that one of the messages I'm trying to get out to people is please correct your experiments for the changing tidal gravity at your station. And then this is, you can't see it, this is just April. And so this is changing over the whole period of the year. And it's the rate of change of the clock at that location. And what I did was express this in terms of the, that's the total potential. Here's what's going on though. I did this in terms of the index of refraction, which your experiment might be able to tease out. What you'd have to do is compare your measurements on a fairly long basis to the atomic clock networks, and because you need a reference for someone to say, well, what's the universal clock like there, and then you can see the difference from that, and it should show up. There's a lot of this is I do every day, but I don't talk to anybody about it. I just do the calculations and try to keep track of things. So anyway, where am I? Okay, let me just show you this. So this is kind of so imagine, this is 10 to the minus 8th. So I did 1 minus the index of refraction there. Okay, so of the vacuum. So I'm basically looking at the vacuum properties because of the changing gravitational potential there. And then, so this is a very tiny residual there, that the velocity as a ratio, the velocity of light there is smaller. So, so it's trending downward, and what I did was accrued again. I stuck a second order equation, so this is just a quadratic to go through here. You can do way better than that, and I don't have time. It's actually early in the morning here. I don't have time right now to do this, but this fits 0.99, 0.9999 is decent for a fit here. So anyway, so that's there. I subtracted that, and then this is what you're seeing. So there, I don't know if it actually is wobbling like this, but the daily variation is what I want, the message I wanted to give you is that, you know, this is going, let's see, so -4 here to 2. So that's, it's, you know, total range is 6 times 10 to the minus 13th. So 3, half of that, 3 times 10 to the minus 13th on a sine wave, basically, is what you should see in the change of the index of refraction. If in fact this is correct, let me show you how I got to that. Okay, let me get this out of the way for a moment. There. Okay, this is just the standard thing. This is actually getting better over time. I've seen several iterations of this. Now the GPS network has to make these corrections. So the people that are doing that are gradually converging to better and better corrections because they have practical consequences. And so, you know, when they're doing this, we're trying to get it close. Now you can ignore all the velocity terms there because I'm talking about a stationary, you know, location. There are probably terms because of the changing velocity of the Earth in the orbit, but that's actually absorbed in the potential. So if I do that, basically I'm putting the potential term in, and then there. And so that's this term. Now what I did for what I showed you, I multiplied both sides of this equation by c. So over here this becomes c times this delta, which actually makes this term c times this is the let's see if I can explain, is going to be a velocity, and it's going to be reduced by a tiny fraction. And I think that that's probably correct, that it's that it's the index of refraction, the inverse of the index of refraction. So normally this is 1 over this. Sorry, I'm really tired. Okay, so and this term in here, the u, is just this 2gm over r. So the actually this term is there. So multiplying through by c, the c squareds on the bottom drop off. Throw all the velocities away, and you just get a very simple 1 minus the potential, term. Actually, you get c squared minus the potential term. C squared, if you go through Mach's explanation, and you take the potential from the Earth is moderately small. If you take the potential of the Sun at the Earth, it's bigger. If you take the Milky Way galaxy at the Earth, it's bigger still. And if you keep going out and adding matter from all the universe, eventually you find that it adds up to the universal potential, which is c squared. I haven't found any good reason to go up or down with that. The Big Bang people are constantly trying to adjust the value of c squared at different times or different locations, but for this kind of thing, you just put c squared minus the potential, twice the potential, and then take the square root and get this number, plug it in, and it should be pretty closely related to your, or relatable to your index of refraction changes there. So I'm not trying to be too exact here because I just want to get you a rough idea what might be going on. And so here, this is the Jet Propulsion Lab Horizon web interface, and it's rather easy to use once you know what to do. But I set it to generate vectors for the Sun, centered at, in this case, I just used the Google Maps. I just went to Google Maps here, and you see that it has the longitude and latitude and longitude and height in meters, and then I just did it for the month of April by minute. The superconducting gravimeters in most of the seismometer networks and magnetometer networks on the Earth all use basically 1 second as their fundamental quantity, and then they publish the minute data for the most part. And all of that, I'm trying to now, I'm working, actually, I didn't want to because it's so messy, but I am tackling the magnetometer network to see if I can't use the same basic approach to do that. The slow diurnal variations in the magnetic field should show some connection with the sun and moon changes, but it's complicated because it looks like the magnetic potential and the gravitational potential are intertwined in some way, and I haven't been able to sort it out yet. It took me about 1.5 years to do the superconducting gravimeters, and then I've been at that for almost 12, 15 years. And then it took me another year to do the seismometers, and I've just started on the magnetometers. And there's so many instruments and techniques now for measuring gravity and the changes in the potential. I've been distracted trying to figure out what to do. If I feel bad because a bunch of experiments are going on and people aren't correcting for gravity at all. They don't even seem to have a notion that it's important. And then, if once you get down in the 10 to the minus 12th, 10 to the minus 15th range, the picos and the femtos, and almost every one of them probably needs to be correcting for this. So anyway, so I do the sun, the moon, and the earth. And then, let's see if I can, where did I put the sheet? Oops, that's that one. Sorry. Okay. So this gets a little tedious. It's not too hard. So anyway, this is the raw data from a run. This is the X, Y, and Z location in Earth-centered coordinates, Earth-centered equatorial. I'm going to call it J2000 coordinates for the moon from the point of view of the station. Here's the location of the sun from the station. Here's the location of the Earth. This seems odd, but it's actually useful. The location of the center of the Earth from there. I also look at X, Y, and Z. So these are this is the vector representing. There's a vector pointing from the center of the Earth to the moon, a vector from the center of the Earth to the sun, and then these are all the distances involved from the instrument to the center of the Earth, from the instrument to the center of the moon, from the Earth center to the moon, from the instrument to the sun center, from the Earth to the sun. You have to use all of these. These are the calculated accelerations, breaking it up into vector form, putting it together. I'm in the middle. I was doing this example for somebody who's building a gravimeter, and they're just getting to where they can detect the things. And I was trying to give them a spreadsheet to do the whole calculation, including the centrifugal force, and I got stuck in the middle. I didn't quite finish it. But for your example, so anyway, those are all that. For your example, I just took the GM for the sun, divided by the distance from the station to the sun, the GM for the moon, and divided by the distance from there. Now, I don't know if there's a differential, we call in the doing the potential this way, the same way there is with the acceleration. With acceleration, you do the direct uh, acceleration on the station, and then you subtract the acceleration on the whole Earth, and because we're stuck to it. And I don't know if the potential works the same way. So part of what I'm trying to do, if I can get somebody to measure based on the potential, measure the clock changes this way, and measure the magnetic energy density changes. Oh, I'm jumping around in here. So anyway, I calculate here sun, moon, and Earth potentials, add them all up. Phi is normally the symbol for the potential. I stick it into the time dilation equations, calculate 1 minus the index of refraction at your location. I did the regression, I estimated it, and then I calculated the delta. And so that's what the signal is. It's a big sine wave, roughly, I guess, for the whole year. And in April, it's pretty well. It's actually quadratic. There's a little bit of curvature there, and then this is roughly what's happening. So there's this sinusoidal variation in there. So your index of refraction should be changing that way. So and if you're trying to measure that, can you detect something like this? That's kind of a question. Let's see, what was in here, the time dilation, any this is in joules per kilogram, right? That's the potential unit. So the energy density is joules per cubic meter. And what I don't have is a way to relate this to. I don't know if that's even a good way to go or not. But I'm certain that the energy density, like the magnetic energy density, the electric energy density, and the gravitational energy density, are all part of the same process. And if you were kind of tending that way, and this vacuum birefringence is sort of edging that way, the way it's all done is similar. And the question is how do they all fit together? The only way I know to go about that is to see if like one of these experiments could actually measure the change in there, and do the magnetic, basically do the gravity measurement, because you should be able to just because you're focusing on it so closely, pick up and do the gravity part first, and then go check the much smaller b squared term. Now, if that variation in there, I keep losing it. Let's see if this variation, let's say if this variation, this is down 10 to the minus 13th, right? And this is for the whole gravity component. All right, so keep that in mind, 10 to the minus 13th gravity. Now, the gravity variations, these experiments are only doing 10 to 15 something Tesla, something like that. Well, and this is b squared that has to go in there. But the gravity at the Earth's surface is equivalent to about 380 Tesla. So what you're talking about is 10 over 380 squared. Let's see if I can do that. Let's do it upside down, or let's do it the other way. 380 over 10. If you're using a 10 Tesla field, that would be 38 squared. So we're talking about 1,000th smaller than that. So what does that come out to in that diagram? So these are 10 to the minus 13th. We're talking about 10 to the minus 16th. which is considerably stronger than what you have, which I thought was down in the 10 to the minus 24th or something like that. Maybe I'm looking at the wrong one, but I think you guys are probably going to see a lot more fluctuations in noise. A lot of that low frequency noise is magnetic and gravitational stuff, because I see it. I've had to come to a conception of how the gravitational field and magnetic field work on these experiments, and the best thing seems to be that it isn't like rigid and unchanging, but rather much more flowing and flexible. The signal at the gravimeter station. Let's see if I had that. That was. Oh yeah. All right. It is. I should have kept that one. Let's see if I did. Okay. Here, the signal at the gravimeter stations. You see the changes in here are from like the ocean tides change the gravity at the station by a direct effect. They change it because they're shoving the Earth down, they're moving the Earth, so there are Earth tide effects. But there's also a direct impact on the station. So like ocean waves, for instance, crashing on the beach, some of that comes through a seismic noise, but there are also direct effects. The seismometer networks in the last few years have seen for large earthquakes that the gravity signal comes to the seismometer network at the speed of light and gravity. Gravity and light have exactly the same speed, out to like 14 decimals. That was that neutron star merger back in August of 2017 showed that they're identically the same, and that has huge impact on the sort of thing I've been doing, because anyway, so the signal comes from the earthquake to the station. It's picked up by the superconducting gravimeter network. It's picked up by the seismometer network. The seismometers are just not sensitive enough, and none of them. This is like 1 second data or 1 minute data. That's not anywhere near fast enough to do early warning for an earthquake. So I've been going for almost a year now, trying to locate people who are designing these more sensitive gravimeters to see if they can also sample the data, use the greater sensitivity, don't worry about errors, oversample it like crazy, get up into the gigasamples per second, and then their spatial resolution and will be much better. So right now they're basically, in 1 second they have, they're halfway to the moon in their search space. But if they cut it down to, like if they did it at a giga sample per second, then they would literally be down in closer to a meter. So in terms of searching for the location and size and intensity of the source signal, the gravitational signal from like an earthquake, the density changes from an earthquake or from a tsunami or from something else. So I'm sorry, I'm trying to cram a lot of things in here because there's so much going on. I don't know this. I hate to show you this because I'm so far behind. Let's see. All right, I'm really tired. Can't even spell gravity. Okay. I put some notes out here, gravitynotes.org, and these are all the terms I've been following. I mean, they have every kind of atom gravimeter, superconducting gravimeter, MEMS gravimeter, you know, the the all right, this group in here, they're doing earthquake monitoring, early warning, and imaging. So they're trying to go there. And this is the term that you want to look for, elastogravity. It's kind of a funny name, but there's some people who are tracking the direct gravity signal from earthquakes. Now, your magnetic experiments aren't going, at least right now, to be able to do anything about that. What you could do is provide a base to say, how are gravity and magnetism related, and get things cleaned up on that end, and then in a while, it might be a year or two, or I don't know how long it's going to be, and then we could probably straighten out the magnetometer network and get it to work in conjunction with the earthquake early warning. So here's prompt earthquake detection. There you can see the title, and you can see I'm out of date. This is almost a year out of date, but there's a bunch of people working on that. So and there's a lot of new detectors and all. So here's all these atomic gravimeters in there, cold atom gravimeters, MEMS gravimeters. He's got one. I would like to actually try these and calibrate them on the sun and moon, and just a matter of time and everything to do it. Let's see. This is where I started, the global network for superconducting gravimeters, and then that they're still going on, and that's a nice thing. The Earth models. Okay, this group is pretty good. What they're doing is monitoring the time changes in the precise geopotential for the Earth. So that's the Earth's gravitational potential. So they have like 2,000. It's more than 2,000 by 2,000 spherical harmonic potential. But the important thing, though, is that it's becoming, with the GRACE network of satellite, the GRACE satellites and other methods, they're making this time dependent. So here, time dependent spherical harmonic gravitational potential. So that's really going up. And that's a good conjunction, because you can take these and get your local vertical, the instantaneous local vertical for the instruments in many cases. It's so sensitive with a 3-axis gravimeter of this type, like a superconducting gravimeter, so sensitive that you can solve for the position and orientation of the instrument. You can't do that with the superconducting gravimeters because they're not they're single-axis machines. You can do some calibrations and measurements there, but fundamentally they're single-axis machines. The advanced 3-axis MEMS and atom gravimeter, cold atom and atom interferometer gravimeters are going to have the ability to solve for the position of the sun and moon, and lock to that signal, that complex signal, and and you can solve that then by, basically, it's a very simple regression that you're doing. You're doing a linear regression on each axis. That's all it takes, and then you correct for the orientation and position of your sensor. So it's kind of like a gravitational GPS. So anyway, the implications, if you get a large network And everybody also, if they're calibrated, then they can make an estimate of the position of the sun or the moon holding the sun constant, the sun holding the moon constant, and maybe somebody can help tease out the two. And then you can begin to correct the ephemeris. Okay, so like you can take, this is all coming from the Jet Propulsion Lab data. I have used their Chebyshev polynomials for the positions of the planets and sun and moon, and we probably, without a lot of effort, in a few years, you should be able to do Venus and Jupiter, which are probably detectable. If you have a network of these high sampling rate gravimeters, they actually are the equivalent of like a radio telescope, and or a time of flight imaging system, and you can solve for the direction and distance from which a source occurs. So like if I don't know, I think the gravity still goes in a straight line. I don't know if it's refracted. I don't know if it can be reflected. But at the low frequencies, it pretty much acts like it goes straight through the Earth. But at high frequencies, it looks more and more like ordinary electromagnetism, or varying magnetic field. In my mind, I think of many of the magnetic changes as very coarse-grained changes, and then the gravitational changes are much more fine-grained. So that's just my visualization of it. It just helps me to keep all these different things organized a little bit. This has gotten rather long. I'm just going to stop here. I don't know if there's anything else to say. Let me stop here. All right.